So I got my fancy graphing calculator installed, and this year it looks like a 84 CE, a color edition one, so it's a bonus. Feeling pretty good about that. So I want to show you a couple tricks how we can, just real quick, this is useful stuff, how you could do a limit, like for example this one, using technology. All right, so I do not think I do yet. I'll get some.
No CE. Can you plug it into the wall? No, I need batteries.
Double-A batteries, right?
No, there's no USB.
I'll go get you some of my 84. Dad.
Yep.
I'll go to the store and get batteries tomorrow.
They're AAA.
No, there's some in the office.
Oh.
AAA.
That's not there's some in the office.
Can I run down there right quick and get more AAA batteries? Okay, do you want me to just move?
All right, so everybody go to your calculator. Here's a couple ways you can do this. Let's discuss this. So,
Sorry.
no, you're fine. You're
Are
fine.
you using the next to figure out
Do a little switcheroo on the desk there.
Yeah.
That's a good plan.
Have a bar on it.
Uh-oh. You gotta have a bar.
Mine doesn't have
That's what I follow though.
Okay, so one thing we can do, let's go to the y editor. So y equals, and let's plug this in. So we've got the quantity square root of x scoot right, square root of x minus 2 divided by the quantity x minus 4. Okay, so obviously one thing you could do is you could graph it. So if we go zoom 6, zoom standard, that's not a very convenient window, is it? Okay, so it looks like x is approaching 4, so we don't need such a big window in terms of x's. Let's take our window and instead let's go from, how about from 3 to 5? And remember, if we want the calculator to do the work for us and spread it out on the screen, we can just hit zoom 0, which is zoom fit. So there it is. Oh, look at that. That one actually did put a little hole in it. Ha, amazing. Crazy. So you'll want to go, so just to review, we're going to put the function in there, right? Everybody good there? Then when you go to the window, everybody good with the function? Okay. Then when you go to the window, we're letting x approach 4. So there's no reason to make the domain really big on the window, right? We might as well just go like from 3 to 5. And then the trick that really makes this slick, in order to have the calculator do the work of spreading it out vertically so you can actually see the function better, that's just the zoom 0. So zoom 0, and you see it. Okay, so now what could we do to figure out what the limit is on the calculator? We could trace, right? So if we trace along, as we get close to that hole right there, notice we're getting down, x is getting closer to 4. We're approaching a value that looks like 0.25, doesn't it? Because when we jump over to the other side, we're just a little bit above it, right? So there's one way to do it. That works. That's not my choice. I think there's better ways to do it. I think this takes too long. Instead, you could do this. Now, we've already got y equals in there, but instead of going to the graph, you can go second F2, table set. Okay, and there's a good trick here. So ignore where it's even starting, and go down to independent variable, and I didn't know about this until recently, but if you go down and you change the independent row to ask instead of auto, so hit enter, this is really cool. Now if I go to the table, which is second F5, it makes a spreadsheet and I get to put in the x values, right? That's pretty cool. So then I could make a table of a bunch of x values, but really I don't need to. All I really need to do is just put in something like 3.9999999, and there's the x value. Or I could put in 4, do you have a question? And when I put in, I didn't actually put in 4. When I put in 3 point bunch of 9s, but it rounded it for me. Anybody see that?
Yeah, I got
Okay. And then when I go down and I put in 4.0001 kind of a thing and hit enter, it also tells me 0.25. Okay, so within the ability of this thing to round, it's 1/4. Okay, if I wanted to. I could try some other ones too. They don't even have to be in order. I could do 3.9. I could just type in 4.1. Do you see the huge advantage of this over what we did last year though? Question?
Can you show again how you went to change it to the ask?
Yes. So you go back to second F2, so it's table set, and then you just go down to that row and you highlight ask for independent. You leave the other one alone. Let that one be auto. Okay?
If you change the independent to ask, does that mean you can put in the y value and then x value?
I doubt it. I'm not sure. You go ahead and mess with it and see though. You can explore that later and tell me what it does. But that's pretty handy, right? Then we don't remember last year we had to set the delta x and we had to set what the starting x value was for our table. This is way faster. Just put in the ones you want. Okay? They don't have to be linear. Okay. Okay, other questions? So the technology is pretty useful in this regard. Okay, we looked at all this stuff yesterday, right? Okay, so, yeah, this is where we left off yesterday. Didn't we leave off with that picture right there?
Yeah.
Okay. So, in summary, okay, what we talked about yesterday, in summary, we said that there are 3 kinds of places, common places. These aren't the only places. 3 common places where limits are going to fail to exist. So you tell me, close your eyes real quick. Okay, so what were they? Name them. What's the first kind of place where 2-sided limits, so regular limits, will not exist?
Absolute value.
Like absolute value, you said, right? Hold on, what'd you say? Somebody said, I heard different things. Okay, absolute value, I need more than that. I don't need specifics. I just need, like, what's the function look like? Okay, so good. Okay, so gaps or breaks in the function, right? Approaches different values from the right and the left, which results in a break in the function. Okay, so that's the most common one probably. What else? Asymptotes. Yeah, increases or decreases without bound. Okay, and then the last one is the weird one. That's the oscillating behavior. You don't see that one very much. Okay, there are other ones too, though, and they actually give you kind of a cool example. Now, think what this function would look like. This is bizarre. So this is called a Dirichlet function, after some guy that was both German and French. He was a big-time mathematician. So this is defined as a piecewise function where the y value is 0 if x is rational and 1 if x is irrational. Can you imagine what that looks like? So for example, give me 1 point on this function. Give me the coordinates of 1 point. So I want an ordered pair. Somebody give me one ordered pair that falls on f of x. 2, 0. Give me another one. Pi 1. E1 would work.
Square root of 2, 1.
Square root of 2, 1.
Square root of 3, 1.
Right? And how come? Because those are all irrational inputs, right? See what I'm saying? So quickly, just quick reminder, what's a rational number? Well, okay, but more simply, it's any number that can be written as fraction, right? Any number that cannot be written as a fraction is irrational. As decimals, recall that rational numbers either repeat or terminate. right? Irrational numbers do neither. They're just random forever, right? So do you get a sense here? If you just stop and think about this for any amount of time, this function is going to be ungraphable, obviously, right? Because how could you graph it? If you think you're at like the point 2,0, so is the point next to that going to be rational or irrational?
Theoretically, irrational because one, no, irrational because it would just be 1 over a number of 1s and zeros.
Okay, but how do you know that? There's, in fact, isn't that just a stupid question in a way? What's the point next to it? Is there such a thing?
Uncountable on
No. You could pick one that you think is next to it, and maybe it's rational. But how many irrationals are actually between that one and the other one? Infinite, right? How many rationals are between the two? Infinite. So it's an ungraphable function, right? Obviously, it's discontinuous everywhere. Pretty weird. It's a weird idea, but it's a function. It's defined. It's defined everywhere, isn't it? Right? Strange. Okay.
So you would think the x was even or x was odd?
Well, you could, right? But that's going to be, if x is even or odd, that's going to be, it's graphable, but it's going to have no limits because it's only going to have discrete points separated by gaps anyway, right? I mean, even along the x-axis, if you're skipping from, you're implying integers only, right? Yep, yep.
So it's the difference between a countable infinite and an uncountable infinite side.
Yeah, actually it is. Yeah.
But I'm still confused where we got this.
Where I got this one from?
So points.
Oh, okay, I'm just applying this rule. So f of x, so I'm inputting, these are the outputs, right? So if I'm inputting a rational value, the output's always going to be 0. So if I input 2, which is rational, y equals 0. If I input 1/2, I'm getting 0. If I input 0.3 repeating, I'm getting 0, right? But if I input something that is irrational, like pi, or e, or the square root of 7, the output is going to be 1. Okay?
How would this look if it was like in the y equals?
It never could. That's the only way you can define it right there. It's a piecewise function with those, that behavior.
We did
Yeah.
learn about more piecewise functions.
Yes.
here.
Oh, yeah, we'll do tons of piecewise functions. Yeah.
Are they graphable?
Oh, yeah, most of them are, sure. This is just a particularly weird one. Okay, so that ends